Different hearts, different dreams. Injective souls ignite the beams. No dream alone, no path ignored. Surjective wills knock every door. More hearts to thrive, or more dreams to grow. Two mighty sets now march toward battle. The wings of cardinality raise us high to the heaven of infinity, beyond the sky.
Previously, we discussed how to prove that two sets A and B have the same cardinality by following the definition. That is, we explicitly construct a function f from set A to set B, and then we prove that the function f we constructed is indeed a bijection. The drawbacks of using the definition are evident. First, it may not be trivial to identify a good candidate for the function. Second, even if we are lucky enough to find one, proving its bijectivity can still be challenging. To circumvent these difficulties, we introduce now the following theorem, which is called the Cantor-Schröder-Bernstein Theorem. The theorem states that if there is an injection f from A to B, as well as an injection g from B to A, then the cardinality of A and the cardinality of B are the same. As you can see, the trade-off here is that instead of constructing a bijection, which is more demanding than merely being injective, we can rather construct two injections. Just like in case a fully baked cheesecake is not available, we can order two half-baked cookies instead, and still enjoy our afternoon tea. Let us illustrate this idea with some examples. Our first goal is to prove that the Cartesian product of the set of natural numbers n with itself has the same cardinality as n. One way to show this is by constructing a bijection explicitly, for example, Cantor's pairing function, which maps a pair of natural numbers, m, n, to a single natural number given by the formula h. At first glance, this function may seem unnecessarily complicated, but the underlying idea is quite natural. We are indeed counting elements along diagonals in the infinite grid. The images of the first few elements are shown in the figure, and we leave the audience to prove that h is indeed a bijection. While this bijection is elegant and explicit, it might not always be the first idea that comes to our mind. So let us try an alternative approach. First, define a function f from n times n to n, as below. This function is injective, since the prime factorization of natural numbers is unique. On the other hand, define a function g from n to n times n, which maps each natural number n to the pair n0. This is clearly an injection as well. Now that we have injections in both directions, we can apply the Cantor-Schröder-Bernstein theorem and conclude that the cardinality of n times n is equal to the cardinality of n. Our next example compares two intervals, the left open right close interval from 0 to 1 and the open interval from 0 to 1. The only difference is that the first interval contains the point 1, while the second interval does not. To show they are equinumerous, we can, of course, build a bijection. Here's the idea. Start with the subset of the first interval, called A1, which consists of numbers of the form 1 divided by a positive integer, that is 1, 1/2, 1/3, 1/4, and so on. Now if we take off the point 1, this becomes a subset of the second interval, denoted by A2. Recall the idea of the Hilbert Hotel. We can map 1 to 1/2, 1/2 to 1/3, 1/3 to 1/4, and so on. This shift function is a bijection from A1 to A2. For the rest of the points, which are the same in both intervals, we just match them using the identity function, which is clearly a bijection. Putting everything together, this gives us a piecewise bijection. We leave the audience to check the details. We will probably agree that the construction of this bijection takes a bit of creativity. Yet it's considerably simpler to construct two injections instead. Indeed, we define one injection from the left open right close interval to the open interval by sending x to x divided by 2. The image is the left open right closed interval from 0 to 1/2, which is contained in the open interval 0, 1, thus a valid injection. For the other direction, we just use the identity map, since the open interval is already contained in the left open right closed interval. Now, by the CSB theorem, the two intervals are equinumerous. You have now seen how to apply the Cantor-Schröder-Bernstein theorem to show that two sets have the same cardinality. In the next section, we will continue exploring some useful properties of cardinalities.
信了，天色。